Right, so now we start the exercises on subsequences. So this one, here we have to prove lemma 664. So let us recall the statement of this lemma briefly. We are given three sequences of real numbers. We have to prove that an is a subsequence of itself. That's the first thing. And then if bn is a subsequence of an and cn is a subsequence of bn, we have to prove that cn is a subsequence of an. In other words, we have to prove that this relation, that one sequence being a subsequence of another, this relation is reflexive and transitive on the class of all real sequences. So for reflexivity, we consider the identity function iota from the set of natural numbers to itself. We know already what it is. It maps every natural number onto itself. That is, it does not change anything. And for this notation, see exercise 338. We have already seen this. This is clearly a strictly increasing function in a trivial manner, because it does not change anything, so it is strictly increasing. And also again, because it does not change anything, we have this as well. For all natural numbers n. So that just tells us that an, this sequence, is a subsequence of itself. And recall the definition of a subsequence. For an to be a subsequence of itself, we want a function like this, which is strictly increasing and for which we should have this for all natural numbers n. And that f for us now is this identity function. So that's why we have one half of this lemma. Next, bn. So let us first write the hypothesis, what's given to us. This is a subsequence of an and Cn is a subsequence of Bn. So there exist strictly increasing functions f and g, say, such that Bn is a subsequence of An. So Bn is equal to AF of n, and Cn is a subsequence of Bn. So Cn is equal to B G of n for all natural numbers n. Now the composition of f and g is a strictly increasing function you can see why it is strictly increasing. It depends on the strictly increasing nature of both f and g. It's very easy to show, so I leave that to you to understand, such that Cn is equal to, first of all, and this n now is any natural number. This is Bg of n, but g of n itself is a natural number, so we can use this. Bg of n will be equal to A f of g of n. So that equals A f composition g of n for all natural numbers small n. Hence this is a subsequence of An. And that's just it. This completes the solution. Now, so this relation of being a subsequence is reflexive and transitive on the class of all real sequences. If somehow it also turns out that the relation is antisymmetry, then it will be a partial order relation on the class of all sequences. But that unfortunately is not true, and we see that in the next exercise. In one section of this text which is coming, we will see these things in detail: partial orders, total ordered relations, well ordered relations, Zorn's lemma. These things are coming, and how Zorn's lemma is equivalent to the axiom of choice. antisymmetry says that if with respect to your relation, which you can write like this, say you have some relation under which A and B are related like this. Antisymmetry says that if you have this as well as this, then A and B are equal. We will now show that for this subsequence relation, this is not necessarily true. That is, you can find two sequences of real numbers A and B such that A is a subsequence of B and at the same time B is a subsequence of A, but they are not equal. Okay. So this is our second exercise. Can you find two sequences? AN and BN which are not the same sequence. But such that each is a subsequence of the other. Solution. So we straight away define those sequences. Let AN and BN be defined as this. AN is the nth power of -1 and BN is the n plus 1th power of -1, where the suffix n of course is a natural number. Okay. The function defined like this, if n is defined to be equal to n plus 1, is strictly increasing Okay, now we are going to use this function to show, you can almost immediately see that because of this strictly increasing function, we have the fact that Bn is a subsequence of An. note that Pn equal to minus 1 to the power n plus 1. This equals an plus 1 by the definition of an, and that is equal to a f of n for all n belonging to n. So Pn is the subsequence of an, but also an is what? An is minus 1 to the power n, and this can also be written as minus 1 to the power n plus 2, because minus 1 whole square is 1. Now this is what? Minus 1 to the power n plus 1 plus 1. Okay, so minus 1 to the power n plus 1 plus 1. So this is Pn plus 1. If you take n plus 1 in this formula, you get minus 1 to the power n plus 1 plus 1, which is what we are having here. So this is b of f of n. So you see that the same function f also shows that an is also a subsequence of Pn for thus is a subsequence of Bn as well. However, we still have to show that An and Bn are actually different sequences, which we will just mention because it can be seen simply from the definitions of An and Bn. Note that the sequences are distinct. It is starting from 0. I think I have written 0 everywhere. Yeah. This is not equal to Pn. Equality of two sequences demands that their corresponding elements or corresponding terms are all equal. In this case, that is the furthest from the truth, because no term is in An is equal to the corresponding term in Bn. In fact, An is always different from Bn for all natural numbers n. So this completes the solution and shows that the relation of one sequence being a subsequence of another is not antisymmetric. Then Exercise 3. Let AN be a sequence which is not bounded. Show that there exists a subsequence Bn of An such that this limit exists. Okay, let me write it here. And is equal to 0. And we have a hint for this one. For each natural number j, introduce the quantity Nj, which is defined to be the minimum of this set of those natural numbers for which the absolute value of the corresponding term in the sequence An is greater than or equal to j. And something else. First, explaining why this set is non-empty. Why this set is non-empty. then set Pj equal to A n j. Okay, so we are now going to see the solution, but this solution will be incomplete. Why it is incomplete? That is, it's not because we have been unable to find a solution, but it will let us see what happens if, without thinking of anything, we just follow the hint. Let's see what happens. So within brackets I write incomplete. You will have to complete it. So we start our solution. For each positive integer, for technical reasons, we will take instead of starting our thing with 0, we consider positive integer. For each positive integer j, it is given that the sequence is not bounded, so that means it has no bound. In particular, j is not a bound of the sequence. Is not bounded by j, and that means what? Boundedness means, had this been bounded by j, we would have had this. All these absolute values would have been less than or equal to j for all n, but that's not the case here. So some such absolute value will be strictly greater than j. So that's why this means that this is greater than j for some natural number small n. Okay, and this is why this set is non-empty. Do you see now? For each natural number j, there is at least one suffix n for which this inequality is true. This inequality is true, so that means this is also true. Hence, this set is non-empty. Because we have considered strict inequality, so we are going to consider the according set. Okay, this is non-empty, and that is why we can consider its minimum. Let nj be defined to be the minimum of this set. The existence of this minimum depends on the fact that the set of natural numbers is a well-ordered set under the usual order relation it has, which is something we have not got yet in this text, although we may already know. And for that, see proposition 814. I think it proves the fact that n is well ordered. What that means is this: if you take a non-empty subset of the set of natural numbers, then that subset has a least element, a minimum element, which is an element of the set A, and it is less than or equal to all the elements of the set. In particular, it is strictly less than all the other elements of the set A. The condition is that A should be a non-empty subset of N. And you can, if you want, prove this very easily using induction. Okay, you can find this proof in any good book on number theory, or we are anyhow going to prove this in proposition 814. For now we assume this, okay, because we need this. Without this we cannot move forward, even in this incomplete solution. Okay. And I am having some difficulty today in terms of health, because I am feeling a little feverish, but we will continue. It's not so bad that I cannot continue. We will continue, but I may be somewhat slower than the usual. So at times I am unable to concentrate. Okay, so, and define Pj to be equal to Anj. So far we have just simply followed what has been suggested in the hints. Okay, now we will see what these things give us. Now it implies from the construction of this new sequence Bj, that what do we have? 1 over Bj, 1 over absolute value of Bj is strictly less than 1 over j for all positive integers j. We started our development of everything in this text from the principle of induction, no? And this well ordering principle that I just stated now, this in fact is equivalent to the principle of induction. Each one is a consequence of the other. For all positive integers j. Why? Because you see, Bj means what? bj means anj, and this is strictly greater than j. Why? That is because nj belongs to this set. And in fact nj by its very definition is the smallest element of this set. So you can put nj here in place of n, so you have this inequality and you can take the reciprocal, so that gives you this. And that is why you can see that because we are taking reciprocal, we have not started from j equal to 0, we are considering positive integers j, which ultimately does not affect anything. Okay. So now these inequalities immediately tell us that the sequence whose jth term is 1 over absolute value of bj, this sequence converges to 0. That you can understand by now. You have seen enough analysis to understand that. From this, or if you really want to be rigorous about everything, these inequalities show us that the sequence 1 over absolute value of bj is trapped between the 0 sequence and the sequence 1 over j, both of which are converging to 0. So by the squeeze test, this intermediate sequence also converges to 0. Okay, you can argue like that also. From this, it's easy to see that this limit is equal to 0, since one over absolute value of bj equals the absolute value of 1 over bj for all positive integers j. We in fact have this limit. So the absolute values of the terms of a sequence converge to 0. This tells us by the 0 test for sequences that the original sequence also converges to 0, whose jth term is 1 over bj. And that result is, what was the number? So by corollary 6, 4, 17, it is that 0 test. We have this limit. So in the original exercise, we were asked to show that an has a sequence whose reciprocal converges to 0. But there is a problem here. It seems like we have got a subsequence of an whose jth term is anj, whose reciprocal converges to 0. This limit is true, there is no problem with that. But is this really a subsequence of anj? You may have noticed another problem. If you follow the notations absolutely strictly in the exercise, it is said that it has a subsequence where the index starts from 0, but that is not a problem. You can make this sequence, you can rewrite this sequence in a, here I have written 0, no? It will be 1. You can rewrite this sequence in a way where the index starts from 0. In place of j, you just have to consider j plus 1, that's all. You think of j plus 1 as a new suffix, say I, then I starts from, what I am trying to say is this. Not exactly what I said just now, that is not true. This equals pi plus 1, where I starts from 0. Okay, that's what I am saying. And this bi plus 1, you can give it some other name, say ci. So that gives you a sequence where the suffix starts from 0. But that is not the problem. The problem is in deciding whether this bj is really a subsequence of an. For that to happen, you know that these nj's should be strictly increasing. As j increases, nj should also increase. It should not be the same for two different values of j. The corresponding nj's should not be the same. And in that direction, we see this. Note that should we write about j first? Okay, let us first write what we were anyway going to write. This set, the set of those natural numbers for which the absolute value an is greater than j plus 1 is a subset of the set of natural numbers for which this absolute value is greater than j. Because if this inequality is true, then this is also greater than j. So from this inclusion, we are writing this nj is less than or equal to nj plus 1. Why? That is because nj plus 1 is by its definition the smallest element of this set. That means it is in this set. Nj plus 1 is an element in this set. So because of this inclusion, nj plus 1 belongs to this also. And the smallest element of this set is nj. So the smallest element nj is less than or equal to this other element nj plus 1 in this set. For all positive integers j, we don't necessarily have nj strictly less than nj plus 1. That is the problem. Thus, Bj, which is Anj, is not necessarily a subsequence of An. So that means whatever we have done so far is not actually enough. This may not be a subsequence of An. What is guaranteeing us that Nj is not equal to Nj plus 1? They may be the same, no? The smallest element of this set may turn out to be the smallest element of this set also. In that case, Nj plus 1 will be equal to Nj. So giving us a sequence which is according to the definition of a subsequence, not a subsequence of An. So then what to do? It seems like we have a situation like this. This is our original sequence, A0, A1, A2, A3, etc. and it goes. And now we have An1, An2, An3, where the inequalities linking these ni's are these. We want strict inequality. Now, keeping these inequalities intact and considering a situation where we have not got a subsequence of An, we can say have this. N1 is equal to N2, which is equal to N3. For some time this goes on, okay, some nk, and then you have nk plus 1, and then maybe again some equalities, and then you get some you again encounter some suffix where you have a transition to a higher value, and then maybe again some equalities. You may get a strict inequality here immediately. I mean, anything can happen, but if you have this type of situation, then the corresponding Anj is not a subsequence of An. But note that we can salvage matters even in this situation by not considering all the Nj's, but considering some of them, namely those which are actually distinct. Instead of considering all these ni's, you can say consider n1, and then the next one you consider is nk plus 1. Then you ignore whatever else is appearing here. The next one you choose is nj plus 1. The question is, how do we know that this such an equality, when it is attained, a chain of equalities, ever stops, so that we can consider a next one? Let's see what happens if it does not stop. This is how actually real mathematics goes. I mean, we see the final solution where everything falls in place and it's all nice. But if you really go down to the process of solving a problem, many such situations occur. You have to overcome each obstacle I mean, it takes time, and sometimes it may not come to us at all. For the sake of simplicity, say right from the very beginning we just keep on having equality. That is our sequence, this n i's. The sequence of suffixes is a constant sequence. And it just goes on like this. You can think of this as some positive integer m. All of them are equal, and that is a positive integer m. Then am, okay, keeping in mind the definitions of the nj's, m is n1, so am, which is an1, will be greater than 1, but m is at the same time n2 also, so am, which is an2, is greater than 2. In this way you can see that the absolute value of am must be greater than all positive integers, and this is not possible because the positive integers have no upper bound, and that is a contradiction. So that's why such a chain of equalities, whenever it occurs somewhere among these numbers, it must stop. It should have only finitely many elements being equal. Okay, so you will encounter higher and higher numbers. It will never stop. You will never stop encountering higher and higher numbers. From that you can create, in fact, a subsequence of this anj itself, which will look something like this. anjk is there. K is starting from somewhere. I mean, starting from 1, and the k goes according to how you have the situation. And this also converges to 0, because this is equal to pjk. Think about it. And these njk's actually now are increasing, because that's how we have chosen them. We have the strict inequalities like this. Now we have so this is a subsequence of our original bj, and we have shown that the reciprocals converge to 0. So the reciprocals of these terms will also converge to 0, because this is a subsequence of bj's. So this is a subsequence of 1 over bj's. Any convergent sequence has all its subsequences converging to the same limit. We are using that result, proposition 665. Okay, so this is one way of salvaging matters, which is very messy. I mean, you can understand what sort of situations you have to consider here, and somehow rigorously justify that all these things, okay, in a very nice manner. It is difficult to write such a solution, and it does not look nice at all. It looks like we don't really know. In the beginning itself, we did not know how to proceed. We have just blindly followed one path. Then we came across an obstacle, and we have somehow in a very messy manner come the obstacle. Okay, we have overcome the obstacle in a very messy manner. It looks naive. It looks like we don't really know what to do. So why did Tao suggest such a hint? It's because I think the question of getting a strictly increasing sequence of suffixes did not cross his mind. It may happen. Sometimes things are so familiar to us that we may miss some details, and so we have come to this messy situation. There is another way of salvaging the matter in a very nice manner. It is by modifying those sets themselves. Instead of simply considering these sets, we modify them so that when we construct the sequence bj, from the definition itself it follows that not only are the reciprocals of bj's converge to 0, but the bj actually is a subsequence of an, and that required modification, you will understand what has to be done as we do a similar thing in another solution. So I leave this solution here itself like this, incomplete. So it's left to you to complete. So we will now go to the next solution and the next exercise, and in the course of these coming two exercises, in the course of solving them, we will know what is to be modified here. Okay, so let us now see the next one. In spite of all this, I am still saying that I may have misunderstood something. That maybe these ordinary inequalities nj less than or equal to nj plus 1 actually become strict inequality if we consider something in this whole situation that I may have missed. So please go through the things carefully, and if you feel something I have missed which gives us a simple and easy solution, please let me know. Next, okay, ink is needed. Proof proposition 665. Note that one of the two implications has a very short proof. solution. So here our first job is to recall the statement and then go to the proof of that statement. So the statement is just this. This proposition has that name also, subsequences related to limit. Let an be a sequence of real numbers and let L be a real number. Instead of writing so much, you can write this also. L belongs to the set of real numbers. Then the following to assertions, statements, anything you can write. Statements are equivalent. A the sequence an that is A, no? Yes. The sequence an converges to L, that is L is the limit of this sequence. And part B, every subsequence of n converges to L. And it has been said that one of these two implications, A implies B and B implies A, one of them is almost immediate, which means, oh, we are inside a solution. So we now prove this. This we have written, it does not form a part of the solution. Okay, I am just writing it here for our recalling the statement. Since an is a subsequence of itself, B implies A. If you assume that every subsequence of an converges to L, then we have already seen in the first solution today that every sequence is a subsequence of itself. So that just simply says that the sequence itself also converges to L. In fact, this statement includes A. in it. So that is nothing surprising. What is surprising is that this lone statement, convergence of AN, also says that all the subsequences converge to L. That is what we now prove. We now prove that A implies B. So we assume that this converges to L. So we start by choosing a positive real number epsilon. This convergence immediately implies then there exists a natural number n such that the distance between AN and L is less than or equal to epsilon for all indices n greater than or equal to that natural number n. Okay. Now we do something else. Something else means we are now going to show that any subsequence of the sequence of natural numbers is unbounded, just like the sequence of natural numbers. And we will need that fact in this solution. Our actual aim now is to prove that any subsequence of AN also converges to L. So let ANJ be a subsequence of AN. Recall that this means Nj is strictly less than Nj plus 1 for all natural numbers j, which tells us that Nj itself is also a subsequence of the sequence of all suffixes, all natural numbers. Note that this is a subsequence of N. We now claim that Nj has no upper bound in R. To show this, or in fact we don't really need to consider R. It's enough if we consider the set of natural numbers itself. Okay, we will prove this by showing that M is not an upper bound of the sequence Nj for all natural numbers M, and this we will do by induction on M. To start the induction, note that N1 is greater than N0, N0, and N0 is greater than or equal to 0. The first inequality comes from the fact that this is a subsequence of N, and we in fact have its strictly increasing nature, so we have used that here to write N1 strictly greater than N0, and because all these Ni's are natural numbers, so all of them are greater than or equal to 0. So you see that if M is 0, we already have found a term in this sequence that is exceeding 0. So 0 cannot be an upper bound of Nj. Thus 0 is not So that means our claim is true for M equal to 0. Assume that M is not an upper bound of Nj. For some natural number N. Then An is greater than M. M not being an upper bound of Nj means, Nj, sorry. See, this is how we make mistakes. For some natural number J, this implies nj plus 1. Nj plus 1 is strictly greater than nj, and now because we are dealing with natural numbers, nj greater than m implies nj is greater than or equal to m plus 1. We have already proved this when we were developing the theory of natural numbers from the piano axioms. So we now see that a term of this sequence is strictly greater than m plus 1. Thus, m plus 1 is not an upper bound of nj. This completes the induction. So that means we have successfully proved that this sequence, a subsequence of the sequence of natural numbers, is not bounded above in the system of natural numbers. But now we come back to what we were left there hanging. We have got this thing. We chose epsilon. For that epsilon we found a natural number capital N for which these things are true. So because nj has no upper bound, this capital N in particular cannot be an upper bound of nj. In particular, n is not an upper bound of nj. And so nj is greater than n for some natural number j. Due to the increasing nature of the sequence nj, this implies ni is also greater than n for all I greater than or equal to j, because if we take higher values of I, then those ni's are even greater than nj. So they are, all of them will be greater than capital N also. Hence, and we know that when a suffix is greater than n, that can be put in that inequality, absolute value of a n minus l less than or equal to epsilon. So from that we get this a n I minus l is less than or equal to epsilon for all I greater than or equal to j. There is that intermediate thing which we are not writing here. Because I is greater than or equal to j, ni is greater than or equal to nj, and because nj is greater than n, ni is greater than capital N, and because of that this is less than or equal to epsilon. So for epsilon we have now found a j in the system of natural numbers for which these inequalities are true. So we have proved that the subsequence ANI converges to L as well, and ANI, actually we considered ANJ, but the suffix can be given any name since it's a dummy variable. You can use J here or I or any other letter or symbol. The subsequence does not change. So this completes the solution. It completes the proof of proposition 665. But we do something extra, and this something extra will be used later. We will need this, okay, at one stage. So we continue the solution like this. Although the solution is over, so you can in fact write here, hence what will the implication be? A implies B, hence A implies B. Although the solution is over, we extend one half of the exercise. We claim that, okay, so what we have proved just now is what? That if the sequence AN converges to L, then all the subsequences converge to L. And in the other implication, which was almost obvious, if all the subsequences converge to L, then the original sequence converges to L, simply because the original sequence is also a subsequence. However, we can make another such statement along the same line, which is not like this, which is not this trivial. What we are now going to claim is that if you consider you have this sequence, A0, A1, A2, A3, A4 and so on, this is your original sequence. If you collect the even suffixed terms, you get a subsequence. You collect the odd suffixed terms, you get another subsequence. If these two subsequences alone converge to the same limit, then that is also the limit of the original sequence. That's what we are now going to show, which is not very difficult, but it will be very useful. We claim that, let me just write precisely what I have here. an converges to L if A to I, yes, and A to I plus 1 both converge to L. So assume that this limit is L and this limit is also L. Choose epsilon greater than 0 because of these two limits. There exist natural numbers J1 and J2 such that A to I minus L is less than or equal to epsilon for all I greater than or equal to J1 and A to I plus 1 minus L is less than or equal to epsilon for all I greater than or equal to J2. Okay. Since every natural number is either even or odd, this implies this is less than or equal to epsilon for all n greater than or equal to the maximum of 2J1 and 2J2 plus 1. What is this final statement? We want this inequality, right? We want one such inequality to be true for all n greater than or equal to something, some natural number. So here what we are saying, since every natural number is either even or odd, this happens. So let us separately consider the cases where n is even and n is odd. So if n is even, then n is 2i for some I, some natural number I. Now if this inequality is true, then n has to be greater than or equal to 2J1. So equivalently I has to be greater than or equal to J1. In fact, we don't need equivalence. This implies I greater than J1. But if I is greater than J1, then this inequality is true. But because 2I is n, so absolute value of an minus L is less than or equal to epsilon. If n is even, then we get this inequality like that. And if n is odd, then a similar thing will happen, you can understand. Then n is of this form 2I plus 1, where I is some natural number. Now just like n is greater than or equal to 2J1, it is also greater than or equal to 2J2 plus 1, because it's the maximum of these two. I mean this thing is the maximum of these two, and this would imply that I is greater than or equal to J2. So when I is greater than or equal to J2, this is less than or equal to epsilon, where this 2I plus 1 is an, I mean it is n. So we are getting this, and that's what we want in order to conclude that an itself converges to L. So that completes the whole, I mean it completes the proof of this extra claim. So this limit is also L, and this completes our extended solution. So far that situation has not arisen. Note that thing, which will allow us to modify the previous solution, where we were talking about modifying the definitions of those sets. Now it will arise again. Here also the author gives us a hint, which however if we similarly blindly follow, we will find ourselves in a similar situation from which it's not easy to come out. So now in defining those sets, we will do the modification here itself. So this is the next exercise. Prove proposition 666, and again those hints are given to show that A implies B. Define the numbers Nj. Again they are being called Nj for each positive integer. This time the author himself is taking positive integers. For each positive integer j, by the formula Nj equal to, this time the sets are slightly different. minus L less than or equal to 1 over J. Explaining why the set why this set is non-empty. Then consider the sequence. So here the hint is, the structure of the hint is absolutely similar. Consider the sequence A and J. The more you see mathematics, the more you will come across such situations where notation is abused. The author is saying, then consider the sequence A and J. This, strictly speaking, this is not true, because A and J is a real number, it's not a sequence. But what we understand what he means that it is a sequence in which J is changing, J is varying over the positive integers. Sometimes it's okay, but sometimes it's not okay. If the situation is so confusing, then you have to actually write it as a sequence. I try to maintain rigor even in notation as much as possible. But I also sleep like this sometimes. Okay, so we have to first recall proposition 666. So it's like that proposition 665, its name is subsequences related to limit points. That one was limits and this is limit points. The statement goes like this. The following two statements are equivalent. A L is a limit point of an and B an has a subsequence that converges to L. Okay, so we will now first see how B implies A. Assume first that AN has the subsequence ANI that converges to L. Okay, now we have to choose, now our aim is to show that L is a limit point of AN. So choose a positive real number epsilon and a stage which is some natural number n. We have to show that there is a natural number greater than n, say I, for which the distance between AI and L is less than or equal to epsilon. That will prove that L is a limit point of the sequence AN. Okay, and the thing that is given to us is that this subsequence converges to L. So we are going to make use of that immediately. So for this epsilon, due to that convergence, there exists some natural number j such that the distance between ANI and L is less than or equal to epsilon for all I greater than or equal to j. Okay, this thing we are getting from the convergence. Oh, for the sake of being somewhat to emphasize the fact that this j is something fixed, we are writing j naught. You can keep it j also if you want. Since the set Ni, where I is greater than or equal to j naught, has no upper bound in the set of natural numbers, which of course we have proved in the previous exercise or the one before that. In the previous exercise. The previous solution. We have Nj greater than N for some j greater than or equal to j naught. for such a j, we also have C. When you take I greater than or equal to j naught, this happens. So because our j is greater than or equal to j naught, here we can take j in place of I. An I minus L, this distance is less than or equal to epsilon. So what have we shown? We have shown that for any epsilon positive and any stage n, we are able to find a suffix value greater that exceeds that stage, and for which the corresponding term in the sequence and this is our suffix now, is at a distance from L less than or equal to epsilon. Hence, L is a limit point of An. So we have shown that B implies A. Conversely, shall I have enough time for the converse? Let me just say something. Yeah, hopefully so. Conversely, assume that L is a limit point of our sequence. So now we are assuming that A is true, and we will prove that B is true. So we will now have to construct a subsequence of An that converges to L. And in this construction, we need those things given in the hint, those sets and those nj's. We define a subsequence Nj of the sequence of natural numbers as follows. First, we define n naught. N naught is just how the hint is given. We define it to be this. So here our j is 1. Oh, no, not n naught, no. N B. Okay, we are writing n naught, but we have 1 here. Okay, this suffix that we see here 0, that is 1 less than this j. Okay, fine. Suppose now that ni has been, ni or nj has been defined, ni has been defined for all natural numbers I less than or equal to j, where j is some natural number. We then define nj plus 1 to be the minimum of this set. Cannot possibly write it in one line. An minus L is less than or equal to 1 over j plus 2. I hope it is visible. J plus 2, but there is an extra condition, and n is greater than the maximum of the previous nj's. So the first part of this set is just like what is suggested in the hints, but we have modified that set using this extra condition, because if we don't do this, then the nj's that we create like this will not necessarily form a subsequence of the sequence of natural numbers, and as a consequence the anj's will not necessarily be a subsequence of an. Okay, and this part you can understand what we have done here. The definition you see here is a recursive definition, about which we have already discussed before, and we in fact proved that recursive definitions work. As long as you define the beginning properly in a well-defined manner, and for each thing defined at any stage, I mean these things are defined, okay, that is the assumption here. You define the next thing in terms of this already defined things in a unique and well-defined manner, then the principle of recursive definition says that for all natural numbers, the sequence of things that you are defining is well defined. And instead of going into the details, we make a remark like this. Note that the sequence nj is well defined because L is a limit point of the original sequence and the set of natural numbers is well ordered. Do you see how L being a limit point of an implies that, for example, this is well defined? See, the thing here is that for the fact that L is a limit point of an tells us what? That we can make the difference an minus L as small as we want by choosing anything here, and that too any n can be chosen that exceeds some already given natural number. That already given natural number here is this maximum, and the epsilon that we are choosing here is 1 over j plus 2. So that means there is some n for which this inequality is true and this inequality is also true, and that is why this set is a non-empty set of the set of natural numbers. And then because n is well ordered, this non-empty set has a minimum element. That minimum element is nj plus 1, and being the minimum of a set, it is unique. So that's why this recursive definition makes sense, and we have a sequence at least nj of natural numbers. It's easy to see that this sequence nj is actually strictly increasing, or it seems like we are suddenly skipping everything and rushing forward, but that's not the case. You will realize if you look at this definition that the nj plus 1 is actually greater than nj, or more rigorously, and I want you to do this, one can prove this by induction. The problem that we previously faced in showing that nj is less than or equal to nj plus 1, previously that was not necessary. That now has been that situation now has been changed by this extra inequality. For all natural numbers j, hence anj is a subsequence of an, and this anj will now converge to L. For that we choose some epsilon prime greater than 0. There exists a positive integer j prime such that 1 over j prime is less than epsilon prime, and you already know how this where this is coming from. It's coming from the Archimedean principle. Then anj minus L is less than or equal to 1 over j plus 1. We will say what j is. Okay, we don't see j here because we have j prime, but we will say what j is soon. Greater than or equal to j prime. If j is an integer greater than or equal to j prime, then 1 over j plus 1 will be less than or equal to 1 over j prime plus 1, because j plus 1 will be greater than or equal to j prime plus 1, and this clearly is less than 1 over j prime, which is less than epsilon, and this is coming directly from the definition of nj, the way we have defined it to be the minimum of that set. So that tells us that this is the case. So you see that we have been able to find a natural number, in fact a positive integer j prime, such that starting from that stage onwards, these distances are all less than epsilon prime. Okay, so thus the subsequence ANJ converges to L. This completes the proof of proposition 666. It completes the solution, current solution, and it also completes this current set of exercises. After this we have real exponentiation part 2 in the next section. So that will be all in this video for tonight. If you want to say something about these things, you can write in the comment section below, or you can mail me at my usual address. And next Tuesday, coming Tuesday, we have fields from topics in algebra by Herstein. So see you on Tuesday. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.